This is a structure question about path difference. First question, state what is meant by the wavelength of a progressive wave. The term progressive wave corresponds to a moving wave. So this is a single wave. Now this diagram represents a wave front. The question asks to state what is a wavelength which corresponds to just one section. A wavelength is represented by lambda and the unit is meter. So here is where this term comes from. Wavelength is the length or the distance of one single wave. One professional way to answer this question is wavelength is the distance moved by wavefront during one complete cycle. Now on B is a description of this graph. A cathode ray oscilloscope, abbreviation CRO, is used to analyze a sound wave. The screen on the CRO is shown in this picture. A side note here, horizontally, 5 little tiles corresponds to 1 centimeter. Vertically, also 5 little tiles corresponds to 1 centimeter. The time-based setting of the CRO is 2.5 millisecond per centimeter. Determine the frequency of the sound wave. A note here, not related to this question. Sound wave is a mechanical wave which relies on the particles in the media to propagate. Also, a sound wave is a longitudinal wave, which means that the particles in the medium moves back and forth with the direction of propagation. And then you look, well, this is a transverse wave. It's not showing a sound wave in this form. You are correct. Even though sound wave is a longitudinal wave and represents of all those dots with a lot of compression and relax the dots and then another compression. But to study a sound waves, we have to convert to the waveform so we can identify easily period, frequency, wavelength, crest, trough, and other variables important to study waves. In this question, the sound wave is being represented by a transverse wave. Note 1. Spot a full wave. To be precise, when measuring one complete cycle, is not a good idea to get when it's cutting half of the tile. So in this case, right here is right on this intersection, and here is right on this intersection. So I'm going to measure one complete wave between those 2 points. So let me count how many small boxes I have between those 2 peaks. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boxes. So 10 little boxes is 10 divided by 5 little boxes here. That will give me 2 centimeters, because 5 little boxes is 1 centimeter. I have 10, so it will be 2 centimeters. So that's the distance between those 2 crests, which is 1 wavelength. So I'm going to highlight here with my green marker. Another note, you could pick from here, from this trough to this trough, or from here, from this crest to this crest, will not matter. You pick any wave you would like to work with. Now, in this case, one wavelength corresponds to 2 centimeters. So, what will be the period of this wave? Period is for one complete wavelength. So, the period is 2 centimeters. I know, looks weird, hang there. There is one more thing we need to do. There is a time-based setting, which is 2.5 millisecond per centimeter. So this, which means that on the axis, the time base is this reference right here. So we are going to use to convert the 2 centimeters into seconds. So what you're gonna do is times 2.5 milli is a multiplier. So times 10 to the minus 3. And all these per centimeters, because centimeter is minus 1. Now, I'm going to cancel centimeters to centimeters. And what is left here actually is milliseconds, right? Milliseconds, 10 to the minus 3 seconds. So now I have converted to seconds, which is the unit for period. So period is 2 times, what is left is 2 times 2.5 times 10 to the minus 3 seconds. And this is 2 times 2.5 negative 3 is 0.005 seconds. So that's the period of this sound wave. Now the question is asking what is the frequency of the sound wave. So all this was kind of prep work to find the frequency. So you know the frequency is the inverse of the period. So the period is 0.005 seconds. Remember the unit for frequency is 1/second, which is hertz. So this is equal to 200 hertz. So the frequency is 200 hertz. So this is the second part of the story. The source emitting the sound in B, the question B, is at point 8. Waves travel from the source to point C along 2 different paths, AC and ABC. As shown in this picture, and this is a reflecting surface. So the sound is going to hit this reflective surface and is going to bounce back like echo. Distance AB is 8 meters and distance AC is 20.8 meters. Angle ABC is 90 degrees. Assume that there is no phase change of the sound wave due to the reflection at point B. The wavelength of the waves is 1.6 meters. Let me try to dissect this question and start with the source emitting the sound in B is at point A. So let's assume that there is a, let's say, a sound source, like a speaker, right here, emitting a sound. Then this sound wave is going to have 2 paths. One is going straight to C. To illustrate, that's the idea. So this sound is going to travel as a wave from A to C. Then some of the sound wave is going to travel from A to this reflecting surface. Then it's going to travel in this direction to point C. So both waves that is going to be split right here is going to meet with different paths right here. So C is where both waves meet. The constant phase difference, roughly what means is that if one wave, let's say the wave A the wave A, C, and this is the wave A, B, C. What happened is that if there is a phase difference, which means that all the time they are gonna be lagging with the same difference between both waves. And in terms of the distance, since both waves they meet here at C, looks like that the wave from A to C arrives first, and then this one arrives later because it has a longer distance here. Okay, so now let's answer question CI. Show that the waves meeting at C have a path difference of 6.4 meters. And this is the confusing part, because here on this highlighted yellow say, assume that there is no phase change. And here is asking for the path difference. So how they are related? Phase difference and path difference are the same thing. The phase difference is the distance between two waves or 2 points of a wave in degrees. And the path difference is the same thing, is the distance between two waves or 2 points on a wave, but in length. So this is in degrees, and this is in meter, centimeter, or any unit in the metric system. So now let's answer this question, CI. Show that the wave meeting at C have a path difference of 6.4 meters. So in this case, the path difference is the difference in distance of the path of ABC minus AC. So the distance AC is provided and the distance AB is provided, but I don't have the distance from B and C and need to be calculated. The problem says the angle ABC is 90 degrees, so I can use Pythagorean theorem to calculate this side of this right triangle. So I need to calculate the distance BC. So this is my hypotenuse, which is 20.8 square is equal to the sum of the square of the sides of this right triangle, which is 8 square plus BC square. So in this case, my hypotenuse is 20.8. So this is square, which is equal to the sum of the square of the sides of the triangle, which is 8 square plus BC square. I'm going to rearrange the formula in terms of BC square. So is 20.8 square minus 8 square. So now my BC is the square root of 20.8 square minus 8 square. Ready to plug in the calculator. Okay, so 20.8 square minus 8 square equal square root is 19.2 meters. Now back to the problem here. My ABC distance is 8 plus BC, which is 19.2, minus AC, which is 20.8. So 19.2 plus 8 is 27.2 minus 20.8. So my path difference is 27.2 minus 20.8, which is 6.4 meters. So here I use basic algebra to prove that the path difference between both waves as they arrive at point C is 6.4 meters. And all this for 1 mark. CII, explain why an intensity maximum is detected at point C. Intensity maximum for sound is a louder sound. This will happen only if at C we have a constructive interference between both waves. The wave with path AC arrives first. The wave with path A, B, C arrives behind, later. But anyhow, they meet here at point C. To have a louder sound here, which is the maximum intensity, both waves must be added in phase, which means crest of this wave meets with the crest of this wave, and trough of this wave meets the trough of this wave. If we line up AC wave with ABC wave side by side, we can see better. So here is the wave AC, which is shorter, and this is the wave ABC, which is longer. So this wave is 20.8 meter, and this wave is 8 meter plus 19.2 meter, which is a total of 27.2 meter. So the difference here between both waves is 6.4 meter. There is important information here on the explanation for the question C. The wavelength of the waves is 1.6 meter. So both waves have the same wavelength, which is 1.6 meter. So if the path difference between both waves is 6.4 meter as they arrive at C, so 6.4 meter divided by the length of one wavelength, that gives us 4 wavelengths. I'm going to fix my drawing here, not on scale, because the difference between both should be 4 wavelengths. So 1, 2, 3, and then 1, 2, 3, and 4. So the difference between both waves is 6.4 meter, which corresponds to 4 wavelengths. 1, 2, 3, 4. When the phase difference between 2 waves is a whole number, could be 1, 2, 3, 4, so on, that is an indication of constructive interference. So the answer for this question is, when dividing the path difference of 6.4 meter by the size of one wavelength, which is 1.6 meter, the result is 4 wavelengths. This is an indication of constructive interference at point C. Like, let's say this is a C, so we have here the trough meeting with trough, and then crest meeting with crest, which is an indication of constructive interference and resulting in the intensity maximum of sound. Question III, determine the difference between the times taken for the sound to travel from the source to point C along the 2 different paths. In other words, what the question is asking, to convert the path difference in meter to the time difference in seconds. AC wave total length in terms of lambda is 20.8 meter by 1.6 meter, which is 13 lambda, which means this length, 20.8, is 13 times the value of one single wavelength. Likewise, ABC path wave total length in terms of a single wavelength is that the total distance over the size of one single wavelength, so is 17 times the value of one wavelength. So the difference between both in terms of wavelength is 4 wavelength, which is not surprise here. That's the path difference between both waves. The question is, how do I convert this into time? Let's go back from the beginning. One wavelength from this CRO indicates that is equal to the period. So one wavelength is equal to the period. So the period of one single wavelength is 0.005 seconds. So 0.005 seconds corresponds to one wavelength. So now I'm going to do is cancel this out, and 4 times this number should give us the difference in seconds of 0.02 seconds. And this is the answer, 0.02 seconds. Last question, the wavelength of the sound is gradually increased. Calculate the wavelength of the sound when an intensity maximum is next detected at point C. With the path difference of 6.4 meter, I can fit 1, 2, 3, 4 wavelengths in this space. Now the question is saying that the wavelength of the sound now has increased, which means that the wavelength is longer. So we'll fit less wavelength in the same space. To illustrate this, let me use 3 wavelengths, which is less than 4. As you see, with the increase of the wavelength of sound, we'll fit less in the same space. So in this case, I'm just using 3 wavelengths. So this diagram purpose is just to illustrate an example before answering the question. So now in this space of 6.4 meter, I will fit 3 wavelengths. So which means the wavelength size will be 6.4 divided by 3, and the wavelength will be 2.1 meter. Because this is almost a whole number, if we can kind of round to 2 meter, so that will be our next intensity maximum detected at point C. Because remember, the path difference must be a whole number. So the path difference will remain the same, but the size of the wave, the new wave now, instead of 1.6 meter, will be 2 meter. So the answer is 2 meter.